Hello everyone. In this recording, we are going to use an AI. In this video, we are going to use ChatGPT to help us generate a random search algorithm for knapsack problem. And then we try to uh, understand the code line by line, and then do some evaluations to make sure that the code behaves and produce correct answers. And finally, when we're sure that the code is correct, then we are going to use that code for larger instances. So first, we are going to use this pseudocode that we had for random search for a 0-1 knapsack problem, and then ask ChatGPT to generate a Python code using this pseudocode. So we simply copy paste this block, which is the main block of our pseudocode, to ChatGPT. And before that, I'm going to ask generate Python code for the following pseudo code for the knapsack problem. And then we have the code here, and here we go. So we have the Python code for the following pseudocode for the knapsack problem. And then we have sorry, we have this Python code. So as you can see here, we have this def random knapsack, which is actually ChatGPT generated a function for our random search for the knapsack, which sometimes you want to avoid, but it's not a big deal. But and also, for example, in lines like this, for example, that you have the total weight equals to sum of this in parentheses. And so if you want to also avoid these lines of code, which are the compacted version of a for loop, this is actually a for loop. What we do in this for loop for I in range of this, you are going to multiply w index I by x index I, and then at the end you sum all of them together and put them in the total weight. So this line of code is actually a comprehension, as they said in Python, for a list, for a dictionary, for a set or something. So if you want to avoid those lines, you can simply ask ChatGPT to do that. So set please avoid functions and comprehensions. Okay, so in this case, we will have a basic and simpler Python code, so we don't have any function here. And also, if we look at the total weight here, we actually have that for loop for I in range of this. The total weight will be updated using this without having sum or having this line that we saw previous. So now we need to simply copy paste this block of code into the Colab, and we have our Python code. So next step, I'm going to rename this notebook to random search knapsack. And now we need to understand the code line by line. So first of all, this is a random search, and we know that we need to generate random solutions, so we need to generate random numbers. That's why we need to use this random library, and so we import the random library here. And so this is the first line of code, and then we have the values or the parameters of our problem. we need a list of weight, we need a list of values, we need the capacity, and also the maximum trial, because based on the pseudocode, we need to do this for a limited number of iterations or maybe a limited time. So we need this max trials. But if we go to this instance, this is small instance that we have, so I'm going to replace the values that ChatGPT generated with these ones. So here we have this as the weights. So if we go back, we have this one as the weights, and so here, and also for the values we have 6, 8, 9, 10, 13. We have the capacity equal to 10, and the maximum trial is 5. So if we go back, so the values are 6, 8, 9, 10, and 13. The capacity is 10, and the maximum trial is 5. So this maximum trial actually doesn't make sense for even this small problem, but we wanted to start from a small instances and not too much iteration, so we can make sure that the problem actually the code behaves properly, and then we can increase the maximum trial to something more, and even increase the capacity, increase the number of items, and actually use this block of code for larger instances. So when we have this one, and then finally we have n, which is equal to the length of the w, or we can replace it with also v, because these two have the same length, which is actually the number of items that we have. We also can replace it with a simple integer, but to make our code a little bit more general, we are going to define it length of w. We are going to keep this one, because so let's say if you wanted to later have 10 items here, so you need to update this one, you need to update this one, and you also need to update this value to 10. But if you keep this one, you don't need to update this one. It's going to be updated automatically because you changed the w and v before. So then we have the best solution, which is none. We don't have any solution right now, and the best value equals to 0. So if you go back to our pseudocode, so the best value could be anything that is worse than anything that we expect. So because we are multiplying some non-negative values to each other, so none of the objective functions are less than or equal to, it could be equal to 0, but none of them are going to be negative. So that's why we can choose the best value equal to 0, and the best solution at the beginning is nothing. So we don't have anything. We can define it an empty list, but none is more suitable here because it actually doesn't exist. And then we have this for trial in range of max trial. So this is for the outer for loop that we have, so which is corresponding to what we have here for trial 1 to max trial do something. Okay, and so this is our outer loop here. And so how many times we are iterate and go through this loop? 5 times, because the maximum trial is 5 and the trial is 0, 1, 2, 3, and 4. So 5 times we are going to go through this loop. So you can see here we have a comment here that generate a random binary vector x, which is from 1 to n. N is the number of items that we have, and if you go back here, n equals to length of w. So in this line we have x, we define x as an empty list, and then for I in range of n, which means we need n random values for n items that we have in the list, x, which is an empty list, dot append a random dot rand int 0 and 1. So okay, what does this line of code do is actually generating random numbers, either 0 or 1. So if we go to another cell here, let's see what it actually does. So we need, let's have a for loop for I in range of 5, print, so let me first import random, and then we have the print random dot rand int of 0 and 1. So first we import the random, and then we are going to have 5 random numbers, either 0 or 1. So when you use the rand int, first of all, the output is an int. You have the rand int, so it's going to generate a random integer, and this is going to be between 0 and 1, 0 and 1 included. So the numbers are going to be either 0 or 1. So if I run this line of code, so you can see that we have 5 numbers, 0, 0, 1, 0, 1. If I'm going to run it again, so we have 2, 0, 1, 0, 1. If I run it again, it's now 0, 1, 0, 1, 1. So every time that I run this line of code, it's going to generate a random sequence of zeros and ones. So none of them are the same. So here, for example, in this case, we have 4 zeros. So as you can see, if you run it by yourself, you can see that all the time they are going to be different. So in this case, if we want to see how our code behaves, we need to make sure that this sequence is fixed. What do I mean? Because let's say later we wanted to evaluate the objective function. So every time that I go through this, it's going to generate a random sequence of zeros and ones. And if I wanted to make them fixed to see, okay, if 3 times, or let's say I run this code 5 times, in the 5th time and in the first time, the sequence of these 0 ones should be equal. So I make sure that every time I'm dealing with the same solution. So I don't need to also counter the randomness in my problem. To do that, we need to use this line of code, the random dot seed, and I actually used it before when we have that math quiz for logarithm. So I already showed you this, how to use this one. So the only thing that you need to do is to fix the seed. So let's say it could be any number. I'm going to use 13 here, and now if I'm going to be here and do the same here, so first of all, I'm doing this. I'm importing random here and having this random seed here because I don't want to run this block of code. That's why I have this one here. If I run this block of code, I don't need to import random here again or have the random seed here again. So I'm just doing this because I don't want to run that block of code. So now I fix the random seed equal to 13, and now I'm going to see what is the result. If I run it, now I have 1, 1, and 3 zeros. From now on, it doesn't matter how many times. Whenever I run this line of code, the output is going to be the same. 2, 1, 3 zeros. If I run it again, 2, 1, 3 zeros. Run it again, 2, 1, 3 zeros. So now by fixing the seed, I'm sure that the randomness is isolated. So it's no longer a factor for changing the behavior of my code. Okay, so in this line, we first define the x as an empty list, and then we use this one to generate a random solution. One thing that you can also do here is to use the print function whenever you want to see how your code behaves, and make the rest of the code as a comment that make sure that the rest of the code is not going to be executed. So for example, in this case, if I want to see how this code behaves till here, we can make a comment here, and you can use three double quotations here, and also, so the rest of the code is going to be a comment. If I'm going to use those things here again, everything between these two double quotations now is a comment. So this print and this print now are part of my code. So you can see that we only activated this part, and let's see what will happen if we run this line of code. So when we run this line of code, the best solution is none, because we didn't actually do anything. Okay, so we only generate a random solution, and the best value is also 0. But one thing that we need to do here is that after printing this one, I wanted to see what is this the x. So I'm going to print x. So this x is actually the solution. So every time, so we have 5 trials, the max trials equal to 5, and we also need, so we can expect that we are going to have 5 different x's. So let's run this line of code again, and here we go. So this, first of all, we have 5 x's. So x1, x2, x3, x4, x5. So we have 5 trials, and the first one is 1, 1, 3 zeros. Okay, so because you can see here, the first one is always 1, 1, 3 zeros, because we fix the random seed, and this is equal to 13 in both block of code. So the first 5 generated numbers are going to be 2 ones and 3 zeros. The next one have 5 zeros, and so on. So we have 5 different solutions that they are randomly generated, so they are not the same. And so because we didn't do anything, so the best solution is also none, and the best value is also none. So now we can see how our code behaves. So far so good. So we have 5, as we expected, different solutions. All of them, the length is equal to 5, and all of them, all of the items are either 0 or 1. So this one so far is good, so we don't need the print. I'm going to keep the print. Maybe we can do some comparison later, but now we go to the next line of code. Let's get rid of this part and also this one. So here we go. We have this compute total weight. Now that we have those 5 solutions, so for each of them we need to calculate the total weight to make sure that if that solution is feasible or not. So first we define a variable total weight is equal to 0, the same as what we did for the exhaustive search. And then for I in range of n, which means we go through all the items, all those 5 items of each solution to update the total weight. The total weight equals what we had as total weight plus wi, which means index I of w, which is the weight, the list of the weight, multiplied by x dot I. What is x? X is the solution, and we are looking for index I. So we actually multiplied each item by its corresponding weight to see what is the total weight. Again, what we can do here is after this for loop, we can go and print the total weight. Okay, so to see what is the total weight, and I'm going to again make the rest of the code a comment and make sure that this is not going to be executed. So now again, because we do not have any assignment to the best solution or the best value, these two should be, the first one should be none, the second one should be 0, but here we can see if the function correctly calculate the total weight of each of those solutions. So again, look at those 5 solutions, 2 1 3 zeros, again 5 zeros, 101, 2 zeros. So the next time that I run this line of code, those exactly we are going to have those 5 solutions. Why? Again, because we fixed the C. So let's run this line of code again. We have 2 1 3 zeros, and what is the total weight? What is this value? 5 is the total weight. So how we can make sure? We can go to this one and say, okay, it was 2 1s 3 zeros, which means we have these 2, so the summation is equal to 5. The rest is 0, so the total weight should be 5. The next one, we have 5 zeros, so the total weight should be 0, which is correct. Then we have 101 2 zeros. If we go to the W, 2 plus 4 equals 6, and so the total weight should be 6. The next one, we have 111, so we have 2, 5, and 7, so the summation is equal to 14, so this is also good. And then we have the last one, 101 10, so which means 101 2 plus 4 6 plus 5 11, which means this is also 11. So far we have a code that can generate 5 different solutions, 5 random solutions, and also can correctly evaluate their total weight. Then what we need to do, see this block of code. So if the total weight is less than or equal to C, which is the total capacity equals to 10, then we can see that here we are going to see we put the total value equal to 0. So this is for checking the feasibility. If the answer to this expression is true, which means that this, the solution is feasible, so we execute this block of code. Otherwise, we just ignore that solution and we do actually nothing for infeasible solutions. So here we go. So again, if we go back here, based on the C equals to 10, these two solutions are infeasible. The fourth one and the fifth one are infeasible, okay? So we're actually ignoring them in this part. And then if they are feasible, we define another variable, total value equals to 0, and the same as what we did for the total weight, now we are going to update the total value for feasible solutions, vi, v index I multiplied by x index I. And then we check here, this is the part that we can check this one. So let's see if, again, I think it's a little bit maybe simple, but what we can do here is to, we can do here before doing this, I'm going to do something here. If the total weight is less than or equal to the C, which means that the solution is possible. So I'm going to have this, add this line of code, print the solution is feasible. And then I'm going to add a line of code here under this if, and I'm going to add else, and I'm going to have print the solution is infeasible. Okay, to see what is going on here about different solutions. And then when the solution is feasible, and we go evaluating this one, we are updating the total value. And then I'm going to do, after this one, the same as what we did previously. I'm going to print the total value. And for this part, I'm going to this a comment. And so we also have this one. Okay, let me do something because I wanted to do this one. You can also make them comments using this one. Okay, so now we checking this if the solution is feasible, then we evaluating or calculating the total value or the objective function. If the solution is infeasible, then we print the solution is infeasible. And then we also don't need this one in, again, because we don't have any assignment for the best solution or the best value, we expect the same solutions, which means none for the best solution and 0 for best value. So if I run this code, line of code again, we have the same solutions. So we have the 5, the solution is feasible, and then the 14 is the objective function of this one. So if we go back to V, we have two ones and 3 zeros, so 6 plus 8 is 14. So the objective function is 14 for this solution. The total weight is 0, the solution is feasible, and the total value is equal to 0. And then we have this solution, the total weight is 6, so the solution is feasible, and the objective function equals to 15. And then we have this solution, the total weight is 14, the solution is infeasible. The next one is this one, the total weight is 11, and the solution is infeasible. One thing that I can do here is to make it a little bit easier for us to read. For the last part is this one. Instead of printing X, I can here say we have the solution, print, I can print here, the total weight is something like this, and here we can say the same thing. Need to separate them, and also you can see here the total value, or I can say the objective function, or the total value is better. The total value is this one, total value. And then this is the last part that we want to check, so I'm going to make them like this. So if the total value is better than the best value, so the best solution, we are going to copy the best solution in the best solution, and then the best value is going to be the total value. Okay, so this is actually have a comment here that is going to copy the vector here, which is the least that we have, which is the best solution. And therefore we can now run this line of code to see what is happening. So the first solution, the total weight is 5, the solution is feasible, so the total value is 14, and this is done. This is the next solution, the total weight is 0, the total solution is feasible, the total value is 0, and this is the next one. And finally we go through all of them. So one thing that I can show you here to better understand the process of the code is here. So when we have if the total value is this one, we are going to do this, and we're also going to see if this one actually updated or not. So I'm going to print the best solution, and also print the best value. Okay, so I'm also going to do this one. So every time that if the best solution or the best value are updated, so I'm going to print them. So if you make sure that what is actually happening. Okay, so I'm running this line of code again, and let me do something. I'm going to make it the current best solution is this one, and here we have this one. The current best value is this one. Okay, now let me run this line of code again. So here we go. So the first solution is this one. The total weight is 5, the solution is feasible, and the total value is 14. Now, because this 14 is greater than or equal, or we just check the greater, it's because this one is greater than 0, which is the initial value of the best value, so we need to update the best solution. So therefore, the current best solution is this one. It's not none anymore, and the current best value is 14. Okay, the next solution is this one, 0. The total weight is 0, the solution is feasible, and the total value is 0. And as you can see, because 0 is not greater than 14, there is no update in the best solution or the best value. That's why we don't see those two lines of code here anymore for this solution. We simply go to the next one because this solution is not better than what the best that we have so far. Okay, this is the other solution. The total weight is 6, the solution is feasible, the total value is 15. Now 15 is greater than 14, so the current best solution is this one. We replace 1130 with 10100, and the current best value is 15. 15 is greater than 14. Okay, then we go to the next solution. The total weight is 14, the solution is infeasible. The next solution, the total weight is 11, the solution is infeasible. Therefore, we have the best solution and the best value here. Okay, so this is how these lines of code behave, and so based on what we expect from a random search algorithm, so it's the functionality is correct, and this is what we expect from this line of code. So now that we are sure that this line of code works properly, we can go for example, the first thing that we can do is to increase the number of trials. So far in 5 trials, 15 here was the best value, and this was the best solution that we had. Let's increase the number of trials from 5 to 15, or let's say we increase it to 10, and see how the function behaves. So first of all, we have 15 solutions, different solutions. We are expecting, 10 solutions. And again, the first 5 are exactly what we have seen before. The first one, 2, 1, 3 zeros. And if you remember, we had that 14, which was infeasible, and then we had the 11, which was infeasible. Okay, so the first 5 is the same, and now from 6 to 10, we have different solutions. So for example, for the 6, we have all ones, so actually this is infeasible, so the solution is infeasible. And then we have this one, the total weight is 12, again this is infeasible. Then we have this one, the total weight is 10, the solution is feasible, and the total value is 24. Now, because 24 is more than the 15 that we had so far, so we are going to update the best solution and the best value. So the current best solution is this, and the current best value is 24. Then we have this one, the total weight is 19, this is infeasible. We have this one, the total weight is 16, and so the solution is also infeasible. So from 6 to 10, we had 1 feasible solutions, which luckily was better than what we had. So we have another update in the best solution and in the best value. Okay, so we can see that how this random search works for the knapsack problem. We started from this pseudocode, we converted to a Python code, and we try to understand we try to understand the code line by line and see how it behaves. And finally, we increased the number of trial, the maximum number of trials to see how the function how this line of code behaves. So with this, I conclude this video. Hope you enjoy it.